So yeah, so as Ifan says, thanks for the introduction, Ifan. My name's Stephen Skinner from the Department of Materials, and I'm going to talk a little bit about our interest in high-temperature electrochemical systems, particularly looking at solid state, which is perhaps not a surprise as we're at high temperature. So high-temperature solid-state systems. And so the outline really is to think a little bit about what types of materials we're interested in, what types of systems. So introduce briefly the solid-state electrochemical systems. And then one of the key properties that we're interested in looking at in these high-temperature systems is ionic charge and the transport of that ionic charge through those solid-state materials. Then we'll move on to think a little bit about, well, that's great, we're interested in ions, but how do we directly determine both the rate of transport of those ions through that solid-state species, but also think a little bit about that exchange process of how we get a gas phase ion into the solid-state material and that solid-state exchange process. That then comes in to talk a little bit briefly about partial pressure dependence of measurements, think about how that links to the electrochemical processes. So particularly we're interested in my group in oxygen reduction and a little bit on fuel oxidation. And really what we're interested in is temperatures where we're looking at in excess of 500 degrees C. So high temperature does need some definition. Not everyone would view 500 as high temperature, not everyone would view it as low temperature. So let's be clear that we're looking at very high temperatures in excess of 500, up to probably a maximum of about 1,000 degrees C is the area of interest for these solid-state electrochemical systems. So, no, not quite sure what happened there. So the ceramic electrochemical devices are the types of technology that we're interested in. And so they're conceptually pretty straightforward. So you have primarily three components. So you have an electrode, an electrolyte, and a second electrode. And for most of the devices we're talking about, we have an air electrode, mainly because our oxidant is just static air or flowing air. We don't want to do anything more convoluted in using pure oxygen or anything like that. Increases cost, so it's just static air. And then we have a fuel electrode. So the electrochemistry conceptually is pretty straightforward. I mean, this is very, very basic. So you're looking at hydrogen oxidation to steam and oxygen reduction from the oxygen gas. You're then looking at a membrane that transports those oxide ions across that membrane. So you're reducing the gas on the air electrode, transporting the ionic species through the electrolyte where it oxidizes the fuel, releasing your electrons into that external circuit. So you're using an electrochemical device to generate power. You can use it in the reverse operation where you supply steam to the electrode. The oxide ions move in the opposite direction. You apply load to the device and you're therefore electrolyzing and splitting that water, generating your useful fuel, the hydrogen. And you can do that with oxide ion conducting membranes in the solid state. And more recently what you have is protonic conduction. So you have a solid state material which conducts only protons. And again, you can have a solid protonic fuel cell or a solid protonic electrolysis cell. And so some of those diagrams did not appear. There we go. Right. Don't know why that didn't come up the first time, or did and then flashed away. So essentially, we're looking at these as elevated operating temperatures in excess of 500. The technology is pretty established for fuel cell, less established for electrolysis. That's one of the key development areas. And your challenges are the engineering, the effective interfaces. So these interfaces between electrodes and electrolytes are critical. And also you have aspects of, well, okay, we're running in atmospheric air, but atmospheric air isn't pure, right? You've got all these impurities, sulfur, chlorine, carbon dioxide, etc., and nitrous oxides. What influence does that have on the ability of these things to actually move? And so this is essentially what we're talking about with the device. You're splitting your oxygen, you're transporting the ions, and you're oxidizing your fuel. Okay. All right, so let's assume some background knowledge. So I'm going to make a point that I assume that you will have done some of this in your undergraduate career. Not all of it, but you might have done some of it. So we're assuming that you have an awareness of point defects. So defects at an atomic site in a lattice. So we're talking about vacancies, we're talking about interstitials, those types of species. And therefore, if you're familiar with point defects, you should also be familiar with point defect notation. And point defect notation is typically the Kroger-Vink notation, which allows us to create chemical equations using defects. Okay? We'll also assume, because you've done a couple of these courses already, and you've had some discussion with Jason and so on, and you've done your undergraduate courses, that you'll also have an awareness of what the Nernst equation is, what the Van Hoff reaction isotherm is, some random walk theory, some Butler-Volmer, and general kinetics and thermodynamics. So I'm not going to go over all of that because you should have an awareness of it. I'm going to assume that you have a brief understanding of Breuer diagrams. So Breuer diagrams are diagrams which correlate the defect chemistry of a solid state species with the partial pressure that you're interested in, and that then also correlates to the conductivity of the species. So you can correlate the defect chemistry to the conductivity and therefore predict the charge carriers with their PO2 dependencies. And we'll show a Breuer diagram shortly. Okay. So the key things we're looking at here, okay, so there's your Nernst equation for the cell voltage, so getting the open circuit voltage from that related to the partial pressure of the gas species. You've got the reaction isotherm for the delta G, and we have the low field approximation of the Butler-Volmer equation because we're operating solid state electrochemical devices at low field, so we can linearize the exponential terms. So current density and exchange current density then are simplifying to this relatively simple expression. Okay, you can dig into the background of that at your own pace and your own inclination. And so the key things that we're looking at, and this is something from Nature Materials schematic, that we've got quite a complex set of reactions to consider. So we've said that we've got a simple electrode-electrolyte-electrode structure, but it's not. Okay, so this is the processes, so water absorption, incorporation, oxygen release, proton transfer, so this is a proton conducting species. And you can see we have this composite type substrate here. We've got our particle on the surface. We've got this porous structure. We've got a couple of different materials. We've got various different conducting pathways through the cell, and we have reactions occurring at all of these different points. So you might have points where you have a gas phase, an electronic phase, and an ionic phase coming together, which gives you the triple phase boundary, which is what would limit your reactions. Or you might have an extended double phase boundary if you have a mixed conducting material. So optimizing microstructure as well as understanding the basic electrochemistry is really critical. Okay. So Breuer diagrams and Schottky defects and Frenkel disorder, this is just summarizing the assumed knowledge. So the Breuer diagram, this is an example of a Breuer diagram. So you get the log of the concentration against the log of the PO2. And so you can then generate from your knowledge of the type of defects, both intrinsic, as in Schottky and Frenkel, and extrinsic defects, so those that you introduce into your system, you can generate the regimes and the relationships in the Breuer diagrams. And that then gives you a prediction of how the various different species concentrations will change as a function of PO2. Okay? So then you know what your defect regime is, what your key charge carriers are. So here you have N is proportional to the PO2 to the minus a quarter, so you've got a slope. Okay? You've then got the concentration of your magnesium vacancies in this case is equal to the concentration of your vacancies on the oxygen sites, and so you end up with a relatively flat part of your Breuer diagram, which will tell you that that's essentially your ionic domain. So this area here, that's the charge carriers that are dominating. Okay, over here you've now got an electronic domination because you have these PO2 dependencies. So you can then start to figure out by measuring as a function of PO2 what your dominant charge carrying species is. So is it a pure ionic conductor? Is it a mixed conductor? Is it an electronic? And is it a hole transport mechanism or an electron transport mechanism? Okay. So just to kind of highlight how you can make those relationships work for you. So if we assume empirically conductivity is NQ mu, as we all know, so you're very, very basic. So the number of charge carriers is essentially the concentration of your defect species. So in this case, it's the concentration of vacancies if we're interested in oxygen vacancy transport. So we can start to then link defect notation and chemical reactions to the Breuer diagrams and to the conductivity. So if you have oxidation of iron oxide, again, very basic and not something we're really going to be interested in for high temperature solid state devices. But as an example, you have the oxidation of iron giving you iron vacancies plus some local defects. That's actually not an iron species there. It's actually a couple of holes. Okay, that should actually be a single hole. There's a typo there. And then you've also got the possibility of the oxygen giving you this relationship here. Okay, so you're simplifying from these two expressions to give you the oxygen going to the oxygen and the lattice, the vacancy plus the holes. So that relationship allows you to then assume your defects, combine that with your law of mass action. So you're basically looking at your products and reactants, okay? So you can then assume that you've got your oxygen on your lattice site, your oxygen, your iron vacancies, you've got oxygen on this side of your equation, so you've got a PO2, and then you have your p-type charge carriers. And by simplifying down and rearranging that, you get the conductivity is then proportional to that PO2 to the power of a sixth, okay? So you can then start to link your defect chemistry at the high temperature directly to that Brewer diagram and to that PO2 relationship. So you can now use that predictively. So if you measure your conductivities as a function of PO2, and you've done your defect chemistry analysis, you can then start to think, okay, right, I'm quite happy. I know what my dominant charge carrying species is. Okay. So measuring total conductivity, as in the example of the iron oxide, is easy. You can do a DC conductivity measurement, okay? So you're just looking at a resistance. So you can do that as a function of PO2, and you've got conductivity as a measure of your PO2. Getting ionic charge transport and ionic carriers is a little bit more challenging. So we want to think about how, for these high temperature solid state electrochemical devices, we can probe ion mobility in solids. So I should have updated this slide, so I apologize. So I'm not entirely sure if electrochemical impedance spectroscopy is in lecture 6 and 7. So you might need to look at the program to see exactly which lectures the impedance spectroscopy is. It might be 7 and 8. So whichever ones are electrochemical impedance spectroscopy and the theory of it is relevant here. And we can then essentially characterize predominantly ionic mobility in these solid state systems. So impedance spectroscopy is a really useful technique, because what it will allow you to do is characterize resistance and capacitance, and in the solid state devices you typically get relatively simple, straightforward spectra. So you'll typically have a spectrum which consists of 3 to 4 components. You might have a low frequency component which gives you some information about processes occurring at your electrodes. You probably have a couple of processes which relate to your bulk and grain boundary conductivities. As you go up to high temperatures, as we are with these materials, you tend to lose the capacitive components of those components. So the resistance is then just an ohmic resistance. So you have an impedance spectrum with an ohmic resistance and an electrode component. So you can then start to get some really useful information about your electrolyte and its conductivity, but also the electrode processes and polarization resistance and how that relates to the microstructure. So the impedance spectroscopy is a really useful technique in probing the charge transport in your materials. I will come back to that later and highlight how it can be very, very easily misinterpreted. So I'll finish the lecture with an example of where some fairly well-known, and I would hesitate to, well, I won't hesitate, I will be as blunt as to say Nobel Prize-winning scientists have demonstrably got it wrong. So you have that to look forward to. DC conductivity, typically you're getting a total conductivity measurement. You can use blocking electrodes. So you can separate the charge carrier. So if you know if something is a complete ionic insulator, then you can use that as a blocking electrode. And so you can essentially prevent part of the charge getting through, and therefore any charge that you are measuring is due to the other charge carrier. So you can use blocking electrode measurements. We can also use techniques such as secondary ion mass spectrometry and low energy ion scattering, combined with isotopic labeling to probe directly the charge transport. And this is one of the key things. So impedance spectroscopy, DC conductivity, what you're doing is you're taking an average of all the electrical properties of those high temperature devices, okay? And you're having to say, well, actually, on the basis of probability, we think that's an ion conductor. We think it's an oxide ion. We think it's a proton. We think it's predominantly hole, etc. We can do things like EMF measurements, and we'll talk about that later as well, to give you some separation, but they're not necessarily unambiguous. If you can probe unambiguously the ion transport, then you have a direct measurement of the diffusivity, and through your knowledge of the chemistry of the material, you can convert that diffusivity into the conductivity. And you can start to use that instructively to get some kinetic information about the charge transport. And so this is really just highlighting the complexity in the solid state devices of what we're trying to measure. So typically you'll have potentially bilayer electrolytes, multi-phase electrodes, multiple species at each of the electrodes, and we're trying to understand how we get from these gas phases to these oxide ions and the charge transport through the electrolytes across interfaces and out the other side. So there's lots of exchange processes occurring, lots of kinetic limitation steps, and lots of areas where it's not easy to understand directly what the predominant charge-carrying species are. Okay, so let's look at some example data. So this is going to initially introduce you to the impedance spectroscopy related to an ion conductor. And so this is some work that Yu Zhu in my group has just finished. Completed his PhD late last year and published his work in Chem Matter in the same year. So he was interested in probing electrolyte conductivity of this neodymium barium indate. Okay. So it has an application or potential application in solid oxide cells, possibly in sensors, possibly in batteries, which for the EIS data at least. So what we're looking at here is where we have an impedance spectrum, we can start to extract area-specific resistances. So when we're looking at an impedance spectrum, what are we measuring? Well, we're measuring the impedance, and I've been rather sloppy and not included the units here. So what we have is typically the impedance spectrum in ohms. This is the real part of your impedance. This is the imaginary. Okay, so we have an impedance in ohms, so we can measure that. And when we're starting to think about fuel cell kinetics and thermodynamics, we start to think a little bit about the operation, and we'll start to use current density, and therefore we'll be looking at resistance in area specific, so in ohms centimeter squared. Okay. I hope the projector is going to last. It seems to be flickering a bit. So we can start to extract the area-specific resistance. We can also extract the polarization resistance, as I mentioned earlier. So looking at the low-frequency responses and characterizing the fit to that data and how that relates to the electrochemical performance of the high-temperature device. And therefore, as I said, determine the nature of the dominant charge carriers. And if we then use controlled atmospheres under the determination of ionic species, we can start to extract whether it's a proton conductor or an oxide ion conductor. It's not unambiguous, but it gives you a pretty good indication. So if you use combinations of dry gas, humidified gas, labeled species such as the D2O, we can start to extract that information. So we can see here a couple of examples. So this is a fit to a dry data set. So this is the barium neodymium indate substituted with some calcium. And we have two arcs here. We're starting at 0 at the intercept. So this is effective. We know this is our bulk process. And therefore, this is probably our grain boundary. So we can fit to two RC circuits, so resistance and capacitance, and we can attribute that to the processes within that device. And in dry air, we can do that as a function of temperature, so we can then start to see the difference and the change in that particular process. And we now have an ohmic resistance. So we can see we're no longer intercepting at the origin, so we now have an ohmic resistance. So we've lost probably the bulk component. It's become a pure resistor. So we're now looking for an intercept at high frequency, and that high frequency intercept will then give us this series resistance, which is typically your bulk and grain boundary conductivity as you get to higher temperatures. And then under different atmospheres, you would look for the differences in these species as to whether that is telling you that under a humid atmosphere, you've got a higher conductivity than under a dry atmosphere. Again, not exactly unambiguous, but it's a pretty good and standard way of determining if you have a protonic species. Okay. So that's what we can see here. So we've now done the impedance measurements of these calcium substituted materials under dry nitrogen and wet nitrogen. So if you're doing a measurement there under nitrogen, then you should be seeing a conductivity which is due to whatever species are transiting through your material in the bulk phase. It's probably oxide driven because you'll have some oxygen defects. And when you do the wet, you have an increase in the charge transport. So the only possible charge carrying species that increases in concentration in a humid atmosphere is the proton. So you will therefore have some degree of protonic transport through this. And from the ratios of the total to the wet, so the total dry to the total wet, you can then get an understanding of what the charge transport is, and therefore what the transport number is for the protons in that species. And if you then do the same thing in dry air and wet air, you can start to see that there's a convergence of the data, which is in contrast to what was happening in the dry and wet nitrogen. So the question is then, why are the activation energies different, and why are they converging? So we have to think about what we're measuring. So what we're measuring is the combination of oxide and in the dry, and then you've got oxide and proton in the wet. Okay? So as you then go to higher temperatures, chances are you're dehydrating. So you don't have the protonic charge transport. So you get different mechanistic information in these particular circumstances. Okay? So you can start to interpret from the impedance data and careful fitting and analysis of the impedance data, you can get the Arrhenius expressions and therefore understand what's happening in terms of wet and dry proton transport, oxide transport, etc. Okay, but it's not just about fuel cells, it's not just about electrolysis. We can apply impedance spectroscopy to, for instance, gas sensors, by using pretty well the same principles that we used for the determination of the fuel cell properties. So typical gas sensors, so this is looking at yttria stabilized zirconia material, so YSZ, and it's typically used in quite a wide range of sensing applications. So it's typically used in engine management control. So you want to control the oxygen content in a combustion area, okay? So you can then use this where you're effectively determining the ion transport, so the oxygen transport across the membrane. So you have a reference PO2 in air, and then the probe sits in your fuel stream, okay? So you then have a chemical potential difference across your membrane from a high PO2 to a low PO2. So you have PO2-1, PO2-2, chemical potential on one side of the membrane, chemical potential on the other side. So you have this driving force across the membrane. So that electromotive force that's developed there, you can then relate directly back to the PO2 of your atmosphere. So how does that apply to impedance spectroscopy? So for the impedance spectroscopy, schematically we have a real and imaginary impedance. We have a nicely perfect, well-behaved arc. And what we're doing is we're scanning frequency. So we're scanning from a high frequency to a low frequency. And at the peak of your arc, you'll have an omega max, so your peak frequency. And at the peak of that arc, you can relate that frequency, so 2 pi f to 1 over RC. So this is related to the resistance and capacitance of your circle. Okay? That process has a characteristic time constant. So tau is your characteristic time constant, where f is 1 over tau. And so by relating all of this together, you can define tau for your electrode process is 2 pi CERE. Okay? So from there, we can take that back and link it back to Butler-Volmer equations, the linearized representation. And so therefore, if we can calculate this RE, relating it to the Butler-Volmer, we can calculate the response time, this tau, and in this particular instance, from the data that I had for this particular calculation, we end up with a response time of 10 to the minus 2 seconds. So by using the impedance spectroscopy, interrogating this value up here, you can then calculate this tau. So you've got the response time for your sensor using that impedance spectroscopy. So let's then think a little bit about going back to electrochemical performance of these solid oxide cells. And so what we're looking at here is a typical IV curve. So for the fuel cell technology, we have voltage against current density, and there's your IV curve. Okay, so typically you're looking for open circuit voltages of round about 1 volt, and that's determined by effectively that Nernst equation. You can't get much higher than that. Okay, you can then calculate your power density. So looking at current density, looking at power density. So you're getting the maximum power density is where you want to be operating your cell. But in this particular example, your maximum power density is getting perilously close to this area where you have this drop-off in performance in the IV curve. And so that's due to concentration polarization, and this is due to activation polarization. And those polarization processes are due to gas diffusion limitations, they're due to mass transport limitations, so surface exchange kinetics, etc. This one you can do very little about. This one is essentially your ohmic response. The slope on your IV curve is your ohmic response. So you can do something about that. So you can maximize the performance of your cell. There's very little you can do about the concentration polarization. So now you can simplify this by saying that your cell voltage is essentially your Nernst potential minus your activation polarization, your ohmic polarization, and your concentration polarization. So you can use the IV characteristics to characterize the cell losses in your fuel cell technology. So we can then start to relate those losses to processes, and we can start to relate it to the thermodynamics and the kinetics. So we can start to think about exchange current density from charge transfer kinetics. So we can have an exchange current density term, Faraday, Boltzmann, the molar volume of the charge carrying species, and so on. So standard electrochemistry. So you can then define, and evidently I am skipping many steps here. So if you're not following entirely what's going on, you can be forgiven because I have skipped several steps. Okay, so you can define current density in terms of both electrolyte and electrode losses. Okay. So that current density, you can basically say you have this overpotential or cell loss related to L over sigma. So L over sigma is your electrolyte resistance. And your electrolyte resistance is pretty straightforward. So L is your thickness and sigma is your conductivity. So in terms of controlling your ohmic polarization from your electrolyte component, you can change the thickness, or you can change the materials to have a different conductivity. That's pretty well it, right? So optimizing electrolytes is simple. You can either reduce the thickness or generate a new material with a higher conductivity, or change the temperature to operate at a higher temperature. That's about it for electrolytes. For the electrodes, which dominate these activation and concentration polarization terms, you've now got this term here, which is RTVM NF squared K. Okay, so R and T, pretty straightforward. VM we can get from consideration our lattice. NF, pretty straightforward, which leaves us with K. And K is our surface exchange coefficient, which said quickly is nice and straightforward. It's just the measure of the exchange across the surface. So how do you measure it? So everything else in this equation we can get a pretty good handle on pretty simply. The exchange coefficient might take a little bit more thinking about it. So determining the electrode processes in these high temperature electrochemical devices is really dependent on this surface exchange. So how do we determine it? Now I'm not going to go into the derivation of this either. You'll be very glad to know. So the key principle here is that what we're looking at is a flux of gas species across the surface. So everything around us will have an equilibrium flux across the surface, right? So that's no different to operating these solid oxide cells at high temperature. So at high temperature, there will be oxygen leaving the membrane, there will be oxygen coming into the membrane. That's the definition of your equilibrium at temperature, right? So in the gas phase, using potentially mass spectrometry, or indeed secondary ion mass spectrometry, we can start to think about how do we measure that flux across the surface. Okay? And that's what we want to do. So measuring the flux across the surface is where we start to think about isotopic labels. So now we can create a system where we can label the flux going into the material. Okay? And if we then relate that surface exchange process with the diffusion process and link all of that through to Fick's laws of diffusion, we can then start to solve Fick's law of diffusion for the particular case in the high temperature solid state system where we have a diffusion process and a surface exchange process particularly in a semi-infinite medium. So we have some boundary conditions set up which allow this particular model to work. And so we're now looking at the Crank solution to Fick's law of diffusion. So the C1x is a solution. And so this is relating to the concentration of species in the gas phase, the background concentration of your species, etc. Okay, and then you're extracting the D star, which is your self-diffusion coefficient. And then you also have this H parameter. Okay, but in this equation, you can see that there's no K. Okay, we've not determined the surface exchange coefficient, but we can define H, this parameter in the Crank solution here, as the ratio between K and D. Okay. So if we can then fit our data using regression, least squares regression, etc., then we can extract these H parameters, and from that we can extract this surface exchange coefficient. So we now have the ability, using a tracer, an isotopic label, to measure directly the surface exchange of oxygen into a ceramic material. We can measure it as a function of temperature. We can get the activation energies out of all of that process. And we can then also link it to the diffusivity and therefore the ionic conductivity of that species in one measurement. And because you're measuring it in an isotopically enriched environment, it's unambiguous. Because the only species that you have present in your gas atmosphere is your labeled isotope. There's no other contaminants. So you know that you're getting just that transport species. But it's not straightforward. You need a secondary ion mass spectrometer for a start, and you need some rather expensive isotopes. So there are a few limitations, but there are possibilities of getting that unambiguous measurement. There are other ways in which you can extract these diffusion and surface exchange kinetics. So one of the possibilities is to use electrical conductivity relaxation. So conductivity relaxation relies on a fast switching of gas. So you'll measure a DC conductivity potentially, and you'll measure it under different gas atmospheres. So you'll switch from one to the other rapidly, and as you switch from one to the other, you should see a decay. And that decay you can then fit to diffusion processes. You can do a pulsed isotope exchange, and the pulsed isotope exchange does exactly what it says on the tin. You have a catalyst bed effectively, and you put in a pulse of oxygen-18, and you watch the mass spec response. And you put another pulse in, and you start to see responses. That gives you information about the surface exchange coefficient only. It doesn't give you information about the diffusivity. Okay. There's another technique where you can use temperature-programmed isotopic exchange, which is a variation, and the technique that we use is this isotope exchange depth profile and modifications thereof, because often we're not doing depth profile, we're doing cross-sectional analysis. And that will give you a combination of different types of diffusion coefficient depending on the technique. So you can have the self-diffusion, the tracer diffusion, or the chemical diffusion. And they are not all the same. They're interrelated, but they're not the same. So you have to be very careful in comparing diffusivities whether you're comparing chemical diffusion, where obviously you have a chemical process, so you have a driving force across, you have a chemical potential, whereas in tracer and self-diffusion, you don't have that chemical driving force, you don't have a chemical potential. So the two are linked, but they're not absolutely directly related. And so this is kind of what we're talking about in terms of the Sims type measurements. So you have this flux across the surface, you take your dense ceramic sample, it has to be dense, otherwise you get your gas species absorbing in the pores, and you then have a diffusion profile from the pore into your bulk and not from your surface, which confuses your measurements. You can then either depth profile, so sputter, so it's a destructive technique, sputter into the surface, or you can take a section and look at the cross section, and essentially what you get, and this should have a depth on here. For some reason that's been cut off. So we have a depth profile here, a normalized isotopic fraction there. We fit that to the data, and then we get those kinetic parameters. We can also do that for different types of structure. So we can think about not just bulk ceramics, we can think about thin films. We can think about anisotropic transport. So not everything is three-dimensional. So if we can be clever in how we develop the material, we can use a substrate, we can deposit our thin film on the surface, and we can get a diffusion coefficient through the depth profile, which would give us one isotropic direction. But how do we get the other isotopic direction? So we have to think about blocking. So we talked about blocking electrodes previously. So in this case, we can use gold as a blocking layer to block the ion transport. So now we need to create a section. So we can create the section here. So now the oxygen isotope comes into the trench, and it now diffuses laterally here. So you can then, from essentially the same type of measurement, extract two different types of diffusion coefficient by careful control of how you prepare the sample. So you can get the D in the C direction and the D in the AB direction. And these are the kind of the capabilities that we have, and we can work with you guys on looking at isotopic exchange. This is our dry isotope exchange rig. So you have in here is our sample position. So this is our quartz tube. Over here somewhere you've got some isotopic labels, you've got some research grade oxygen here, and effectively we just pull this down over the isotope exchange sample, heat it for a while, and then all the magic happens and we extract the sample and move downstairs to do the Sims analysis. And so we can label with oxygen 18, H218O, D2O, C18O2. We could do some lithium labeling, and we can, if we've got enough money, do D218O as well. So that gives you different mass species, because in the mass spectrometry, all you're doing is measuring mass. So you then have to interpret the mass. So if you know that the only thing you've put in is mass 18, then there's a fairly good chance that the mass 18 species that comes out is the mass 18 species that you put in, which is the oxygen, right? It's not unambiguous, because again, you can have different overlapping species. So you have to be very careful in the setup in what you're actually measuring, okay? So the Sims instrument is over here. So secondary ion mass spec, time of flight type system, and this is our low energy ion scattering. So we can start to think about how we measure in the outer nanometers of a material. So can we see diffusion and surface exchange processes in surfaces? And this is our newer instrument, the Hi-5 Sims instrument, which will allow us to do simultaneous negative and positive species. So we can measure both ionic types at the same time from the same spot and get down to resolutions of 30 nanometers. So you can then start to interpret grain boundaries. And so do you have preferential diffusion pathways? So rather than just having a bulk diffusion, does it preferentially sit on the grain boundary? Or are the grain boundaries blocked? Do you have contaminants, etc.? Okay. And so this is the first incarnation of the Hi-5 instrument. It's now changed and got this nice new column. So this should be its final format, and it's now being tested and it's just about up and running. So hopefully we'll be getting some data off of that very soon. Other things I want to just touch on. So isotopic labeling and diffusion kinetics are really important, particularly for these high temperature devices. As we move into electrolysis, we now start to think a little bit about We don't operate devices in perfect conditions. So we don't have dry oxygen at our surface for our electrodes. We're going to have, as I said at the start, contaminated air. And of course, one of the contaminants in that air is going to be humidity. So if we do exchanges in humid atmospheres, what difference does that have to our materials? So we can then start to look at this material here, so a lanthanum chromate, perovskite, so an electrode material, which we've measured in humid conditions. So we can measure the diffusivity. So we can create different gas mixtures, so oxygen with water at 30 millibar, oxygen with 0 millibar. And we can measure the diffusivity. So we can measure the diffusivity in the dry condition and in the wet condition. And perhaps not surprisingly, when you think about it, if we're measuring oxygen exchange and we're tracing the oxygen 18 isotope, you would expect perhaps that the oxygen diffusivity in the dry and the wet should be the same, because you're just measuring the mass 18 species. And rather happily, within an error margin, yes, they are. But then we start turning to the surface exchange. And now we see that the surface exchange is not the same. And at the highest temperatures, it's about 2 orders of magnitude slower, which is fairly significant. So by doing the measurements under realistic conditions, with only 30 millibars of humidity, we can really see that the surface exchange in that humidified atmosphere is significantly suppressed. So that has implications in terms of how we interpret data, how we develop devices. Okay? And so we can then start to think a little bit about comparing the data. So here's the diffusion profiles for the 30 millibar data, and here's the data with, so this is pure water, and this is now water in an oxygen atmosphere. And so key things you can note. So same conditions, 900 degrees C, same sample, 0.22 hours diffusion here, 3 hours here. So 3 hours under this humidified oxygen atmosphere, you've got diffusion length down to about 10 microns. Same temperature, significantly shorter time, just in 30 millibars of water, you've now got diffusion coefficient and profile out to 100 microns. So you've got a dramatically different diffusion profile under just water, which leaves you scratching your head for a little while, because why is that then? So we start to think a little bit of what that process means. And what that process means is actually we think we've generated more oxygen vacancies. So because it's just water, you've reduced the sample slightly, you've introduced more vacancies, so therefore you have faster transport of these materials. So it's purely due to the reduction rather than the environment in that particular circumstance. Other things that we can do for high temperature solid state electrochemistry is think a little bit about the surfaces, because we're talking about surface exchange as a key process in high temperature electrochemistry. So looking at the surfaces is interesting. So low energy ion scattering is the technique which allows us to probe that surface. And I'm rapidly running out of time, so I'm going to rattle through this quickly. So what we can do is really see surface segregation in the outer surfaces of your species. So you can monitor the cation species, you can look at the ratios. So this is in one of these perovskite type materials, which is layered. So this is looking at the B site. So this is our bulk composition ratio of nickel to lanthanum, and this is getting out towards the surface. And we can see that we have this enrichment away from the bulk composition, giving us this surface segregation of the B site, but we've got this slight depression of the B site in the outermost surface, the outer 0.1 to 0.2 nanometers. So from that technique, we can then start to say, okay, we have a lanthanum oxide terminated surface, a nickel-enriched subsurface, and then our bulk film. So how does that give us oxygen reduction? Because you typically need a charged species to give you the oxygen reduction. And these are good surface exchange catalysts. So there's a whole series of processes about what does this mean. Is this a dense layer? Is it an amorphous layer? Do you have access for the nickel species through this subsurface? So there's a whole series of questions about how this leads to understanding of the processes taking place. And so effectively, we have this idea that effectively you have the bulk, and you get this segregation of species to surfaces. Okay, can you use that technique to give you ion diffusivity? So this is essentially data that was published by a group in Holland in Applied Surface Science. And so here we can see you have isotopic discrimination in lice. So if you're doing a lice measurement, you can see the oxygen 16 and the oxygen 18. Okay, so therefore you should be able to measure a depth profile. And so the previous depth profiles we've been looking at from the SIMS have been in microns. These depth profiles are in nanometers. So there's a suggestion that in this particular first 3 nanometers in this lice data, there's a potential to get a diffusion coefficient in that outer 3 nanometers. But is it an experimental artifact? So a bit of subsequent thought processes that John Kilner in particular put into this as the PhD examiner suggested that maybe it's not an actual diffusion profile, maybe it's an ion beam mixing, maybe it's a matrix effect, maybe it's an experimental artifact. And it appears that it might be an experimental artifact, but needs a little bit more work to think a little bit about whether we could get something useful out of this by using careful control of the ion beam conditions. Okay, so I'm going to finish up with a cautionary tale. And I realize I'm probably hideously over time, but we started a couple of minutes late, so I'm just going to keep going. So ion charge carrier, we talked a little bit about that. So this material was proposed as a fantastic new oxide ion conductor. So strontium, potassium, silicon, germanium oxide. And you might notice the name on the paper down here. That's all I'm going to say about that, right? So we looked at this and thought, oh, this is interesting. And so this is the data that they published. So reasonable temperature range, really good fast ion conductor, supposedly. We measured it and got this. And we thought, oh, that's alarming. Something's not right. So we thought, something's not quite stacking up with this material. So we thought, okay, let's look at it more in detail. So let's look at the function of the lattice parameters of the potassium content in the strontium site. So no evidence of lattice parameter evolution as a function of composition. So that raised a few flags as well, because if you have a solid solution, you should see lattice parameter variation. And here's all the lattice parameters, and they're all flat. So something is definitely not stacking up here. So then we thought, well, let's do the unambiguous measurement, which I've been banging on about for the last hour. Let's do a SIMS measurement. Let's get the oxygen 18 tracer in there. That'll tell us the conductivity, right? So we do the preparation of the sample. We do an O18 exchange, 70 odd minutes at 740 with platinum on the surface. So we put platinum there as an oxygen reduction catalyst. So there's no possibility that our measurements are skewed by it not being able to get oxygen into the surface. Okay. So we do that, we do the measurement, and we get a diffusion profile just about out to about 8 microns. And from that, we get the maximum diffusivity as being 10 to the minus 12 centimeters squared per second. Now, one of the best oxide ion conductors known at this temperature is ceria gadolinium, CGO, so ceria CO2 substituted with gadolinium. And the diffusivity of that at about the same temperature, 700 degrees C, has a diffusion length of about 600 microns and is about 210 to the minus 7 centimeters squared per second. Okay, well, that's not quite what the paper said. Okay, so if we then think a little bit about Nernst-Einstein equations and thinking about oxygen vacancy, thinking about the conductivities, we end up with a measurement of this total conductivity of 510 to the minus 3, and the calculation of the oxide ion conductivity from that is 110 to the minus 6, which is not what's in the published paper, and it gives you a transference number, or an ionic transport number for the oxide ion of 0.003. So there's a lot of information here saying this is not an oxide ion conductor. So then we do some SIMS. And we look at the SIMS measurement, the total ion, the strontium, potassium, silicon, germanium, etc. And we can see, hey, it's not a single phase. So that raises a few alarm bells as well, right? And then you start to look at the oxygen map, and the oxygen map shows very little transport, and we can see this mixed phase. So what it's clear is that you've got cation segregation, you've got limited penetration, the diffusivity is low. So what does it all mean? Well, it's confusing, because what it means is that they publish data saying you've got an IV curve and you've got a power density. So you've got a claimed IV curve of 1.25 volts. Okay, why is that important? Well, if you calculate the OCV using hydrogen as a fuel at 600 degrees C, as this data was reported at, your maximum OCV is 1.1 volts. So how are you getting an extra 0.14 volts out of this system? Something doesn't stack up. How can it be achieved? So the only way that we could get to that number is if you assume in the calculation that your anode compartment has no water present. It's dry. But you're generating water, H2O, as your waste product. So what's moving? Because it certainly doesn't appear to be the oxide ion, right? It doesn't stack up. So the only possibility to think about is that it's actually the sodium or the potassium. It's the cation species. And actually what you've got is an amorphous phase of essentially an ion-conducting cation species. And by just measuring electrochemical impedance spectroscopy, as they did, they've assumed it's an ion conductor, and because it's an oxide ion conductor. And it's categorically not an oxide ion conductor. And so with that, I am going to stop. There's the summary, and I'm out of time. So I'm not leaving Siva very long to talk, so apologies, Siva. So I'm happy to shut up and let Siva talk, and we can take questions and everything at the end, if that would work better for everyone. Or have the questions now. Whatever works.
Maybe talk to
yeah, it's rather silly one. So I think in one slide you mentioned about the diffusion under humid conditions, and when you said like you might be scratching your head, I'm really doing it now. So I think there's one with water, and yeah, there's
that one or that one.
This one, yeah.
Yep.
So on the left is just water, and
it's
on the
just
right,
water.
yeah,
Yep.
and on the right is water and oxygen.
Yes.
But this is the oxygen diffusion we're talking about.
Yes. Yes. So what I should have mentioned is that these are oxygen 18 labeled. So it's the P H218O.
Okay.
So we're measuring the oxygen transport using the oxygen from the water molecule. Essentially.
Oh, okay.
Yeah.
Oh, yeah. Thank you.
So because what we're measuring is a normalized oxygen 18 fraction. So you know, if there's only water in here and no isotopic label, how do you get oxygen 18 into the system? You're absolutely right. I was not as clear as I could have been.
Oh, thank you. Any more questions?
Well, I have quite a few questions, to be honest. So
we'll take a couple of them, and you might have to come back to me afterwards. Otherwise, we'll be here all afternoon, right?
That's true. Just some general questions, actually. So first of all, I wasn't sure about the experimental methodology of the electrochemical impedance. So First of all, could you please describe a little bit the cell, so I can understand?
Really simple. Well, yes, it is and it isn't, right? So the simplest impedance measurement you can do is essentially you have a dense electrolyte, a dense ceramic, so greater than sort of 90% dense, 95% dense. Thickness doesn't really matter. Thinner the better, because you're measuring ohmic resistance. Deposit a couple of electrodes. Now that can either be the electrodes that you're measuring in your fuel cell, or it can just be platinum or silver or gold or whatever you want. So deposit a couple of electrodes on your electrolyte, a couple of mesh current collectors in your impedance analyzer, 2 electrode measurement, and just get on with it. If you want to do fuel cell measurements, then you might want to do a 3 electrode measurement. So you have a reference electrode in there as well. And then you have to start thinking a little bit about the placement of those electrodes. But it's the simplest way to do it is just the 2 electrode measurement, and that will give you and it's a symmetrical measurement is the key thing. So then you can get away with it being the 2 electrodes.
All right, that was really informative. Can we go to the impedance? You showed some really nice data from your PhD student at some point. Was it a thesis that has been submitted, or? Yeah, these ones. Yeah. So first of all, you said that you start from higher frequencies going to lower frequencies.
Yes.
Is that correct? Yes.
Yes.
So
you don't see frequency in the data plots. So the
yeah.
data plots are just real against imaginary.
Yeah. I was just wondering, why did you, in the methodology, why did you choose to go from higher to lower?
That is essentially the way in which the instruments are typically set up. Is that they always, so high frequency is always at the origin, effectively, okay, typically, and you just scan from low to high. So you've got so you essentially, low frequency is at this point in the spectrum. So each of these data points will be at about 0.01 hertz, and you can scan from low to high, or you can scan from high to low. It doesn't really matter. It's just conventionally the way in which the instrument is set up. It starts high.
Okay.
The data collection times also take a little bit of time. So the data collection at the higher frequencies, the data collection times are relatively short, just a few seconds. As you get down to the lower frequencies, the time per point increases significantly.
Yeah, that's true. I was just wondering because generally I would do both. Because maybe there are some elements that technically you can actually see different things because they happen faster during the scan, if you know what I mean.
Well, typically for these types of measurements, you're looking at the equilibrium.
Okay.
So you're typically not interested in transient species. So certainly for the pure electrolyte measurements, you would let them equilibrate. So you wouldn't measure as a function of time, effectively. You would sit at a temperature for a period of time until that sample had thermally equilibrated, and your response was unchanging, and then you would do your measurement.
Okay.
And then again, you would change temperature, let it get to temperature, equilibrate, repeat. Okay.
All right. Thanks a lot. I still have 2 questions if no one else has.
No, I think, yeah. Does anyone else have a question they'd like to ask?
All right, so I still have 2 questions then.
You still have 2 questions.
All right, so first of all, on the imaginary part of the impedance.
Yep.
I can see there is some resistive behavior at the beginning. So technically, so it starts at the 27 or 30 ohms, let's say.
Yeah, these ones here. Yeah.
So that would be from the current collector, some resistivity from the current collector.
So it's as you go up in temperature, and you're operating at these higher temperatures, you lose the capacitive component from the bulk in the grain boundary.
Okay.
So you don't see an arc for the bulk in the grain boundary as you go to higher temperatures. Okay. So it becomes a pure resistor rather than an RC element. So you therefore don't see an arc associated with the electrolyte or with the bulk or the grain boundary. You just see an intercept on the axis. So this point here is essentially your series resistance, which includes the contacts, the bulk conductivity, and depending on the temperature, the grain boundary conductivity. So you'll have a total resistance here. You can measure the contact resistance and extract that, so then you've just left with your material ohmic resistance.
And that would explain the difference in the starting impedance for each individual temperature, right?
Yes, because this is temperature dependent.
Okay.
Yeah.
Perfect.
So the contact resistance obviously won't be, essentially because it's dominated by stuff outside of the hot zone of the furnace, right? So yes, these are essentially going to be materials properties.
Okay. And one final question, it was a little bit more general one. So coming from an analytical background in electrochemistry, usually I like to see a lot of different tests, like electrochemical tests and experimental methodologies to gain a little bit more spherical understanding, let's say, of what's happening in the processes that are happening in its case. So I was wondering, it's not only in this case, but in general in solid state ionics, I'm only seeing the impedance.
Yes.
I was wondering if it would make sense to see, I mean, I would like to, I don't know if it would make sense to just see the cyclic voltammetry, for instance, or maybe some charges or discharges, since you saw the IV currents as well.
So, I mean, essentially for things like solid oxide fuel cells, you don't really do a charge-discharge process, right? Because it's effectively it's operating in one mode.
Yep.
So you don't have that shuttling of charging and discharging as you have in battery technologies. So doing that kind of charge-discharge cycling doesn't work effectively. As you move into electrolysis, you start to think a little bit about Faradaic efficiencies and so on and so forth. So yes, there'll be a little bit more of that detail. And again, cyclic voltammetry in solid oxide technologies is not used that terribly frequently at all. It doesn't give that much useful information. I think part of that is essentially the types of timescales that you're looking at with the processes. So with battery technology, other electrochemical devices, you're looking at very rapid cycling, charge, discharge, and so on, which you don't have in the solid-state systems.
True, yeah, but technically you can even go with a really low scan rate as well, so you can actually see what's happening over a long period of time.
Yeah,
so
you can.
It's just that basically all the electrochemical processes are quite easy to distinguish, and they don't give you much information of.
I think essentially the key thing is that the CV doesn't, in the solid state, give you an awful lot of information beyond what you can get from these other techniques. And the key thing with things like impedance spectroscopy is we've shown the Nyquist plot, right? But that doesn't give you a lot of information. You have to do an awful lot of extra work with the other representations, and you can start to use the admittance, and you can start to use the frequency responses. You can start to use distribution and relaxation times to really pin down processes. So there's a lot of power in that technique. And I guess one of the aspects is impedance spectroscopy. If you've got the kit, it's pretty straightforward. So, and you can get most of your information from it. So, what do you get additionally from the CV that you can't get about your systems already?
Okay, fair enough.
So what would be the species in the silicon germanium apatite you showed in the good enough?
So the good enough one, well,
we know that it's not oxide ion.
Yeah, so there are two systems. So they've got one which is strontium silicate, potassium germanate, and they've got one which is a strontium sodium silicate. And so we suspect, but haven't been able to prove, that in both of those cases, you have a strontium silicate phase and a glassy potassium phase, a glassy sodium phase. And the glassy phase is likely to be the amorphous phase that has either potassium transport or sodium transport. Because it's pretty self-evident from all of the data, and there's others have published in this area, that you don't get solid solubility into the strontium silicate. The strontium silicate sits as strontium silicate, and that's it. So the amorphous phase is there as the ionic transport species. And the only things that it can be likely to be are the potassium and the sodium.
Thank you.